Hello, everyone, and welcome to this session where we will be looking at how to make technology seamless by leveraging edge-accelerated artificial intelligence and machine learning. My name is Henrik Flodell. I'm the Senior Marketing Manager at Alif Semiconductor. And in this session, I'm going to start by giving you an introduction to Alif Semiconductor. We are a startup silicon supplier, and I assume that a lot of you have not heard that much about us yet. So I want to cover a little bit about our background and what we intend to do. I'm going to give you an overview of our Ensemble and Crescendo families of microcontrollers and what we call fusion processors, which feature both the Cortex-M55 and the Ethos U55 technologies that ARM recently announced. I'm going to go into some detail about how we have architected the Ensemble and Crescendo products in order to be able to maximize the efficiency of AI and ML workloads for embedded use cases. And we have partnered with ARM for this session, and I'm going to hand off to the ARM team and let them run through a live, in quotes, as this is a recording session, of course, but they have recorded the video live demo of our environment sniffing engine in action and show you some of the properties of that engine when it is running AI models in parallel on our device to perform IoT type tasks. And at the end, I will go through some performance benchmark numbers that we have collected during this demo and go over the kind of uplifts that you can expect to see on our silicon with the Ethos U55 compared to CPU-bound processing, and what that means for AI and ML use cases in embedded applications. About Alif Semiconductor, and this is just a brief overview. We have a lot more information on our website. As I mentioned, we are a startup. We were founded in January of 2019. The team is global. We have locations in the US, in India, as well as in Singapore. And what we do is we create microcontrollers and fusion processors for intelligent IoT endpoints. And what we are considering to be unique about our approach to creating these MCUs and fusion processors is that across our entire product lines, we've designed a very technology-dense architecture that cover the 6 bullet points below. Very scalable processing capabilities. Our architecture can scale from a single core microcontroller to a multi-core fusion processor that contain both Cortex-M class and Cortex-A class cores on a common fabric that makes software compatibility up and down the performance spectrum very easy to do. Security, in that we have designed our system from the ground up to be very secure, both in terms of the data that it comes out of the device onto a network, but also data that is being stored and processed on the device. You can think of our security in the same way that you think about a hypervisor. Our secure enclave marshals all of the code that is running on the device, protects access to all the resources like memory and peripherals of the device and assigns them to cores, and also controls the sharing of such resources between the cores. Since we are targeting IoT type use cases, we have connectivity built in from the ground up in our architecture in the form of integrated cellular IoT connectivity, Cat-M and NB1, NB2 cellular, with optional iSIM technology included as well, meaning that you can eliminate a plastic SIM card from your design and run the SIM inside our chip. We have designed both of the product families that we have so far announced to be extremely battery friendly. We have done this in a combination of picking the right technology to achieve low power consumption, but also by doing some pretty innovative design in creating hardware support for performing autonomous power management of the system, which results in a very fine-grained control of exactly what is powered at any given time. We have also looked to the future and decided to enable processing of AI and machine learning workloads across the entire span of our devices to truly be able to realize the use cases that benefit from efficient network edge processing. And we've done this very much entwined with the battery friendliness so that the AI processing becomes something that is suitable for deeply embedded devices as well. And in order to make this very easy to use, we have spent a lot of effort in creating software support for our devices and for this functionality so that developers can be productive with them almost immediately after receiving them. A little bit about our product families. We announced on September 1st of this year our Ensemble family and our Crescendo family of products. The Crescendo family is a family of cellular IoT-enabled devices that also contains a global GNSS receiver supporting all constellations, standard constellations, I should say, worldwide. The Ensemble family is targeting more traditional embedded processing use cases and does not include the cellular or the GNSS capabilities. But with those exceptions, the product families are very similar in terms of functionality. As I mentioned, scalability is very important for us, and you can see that in how we break down the subfamilies of the devices, going from the single core E1, C1 devices, the dual core E3, C3 devices, the triple core E5, C5 devices, and the quad core E7, C7 devices for highest processing performance. Taking a bit of a closer look on how this scalability is realized in the silicon, if we look at the Ensemble family specifically, in our E1 devices, which is configured with a single MCU core, we have a Cortex-M55 core running at 160 megahertz that is specifically designed and configured for low power operation. In addition to the M55 core, we have an optional Ethos U55 microNPU acceleration unit configured to perform at 128 max per cycle paired with this M55 core. If we go up to the E3 device, which is a dual core MCU configuration, we have the same high efficiency M55, but here paired also with a Cortex M55 configured for high performance that can run up to 400 megahertz. And that is paired with an optional second Ethos U55 unit that runs at 256 max per cycle. Moving up to the E5 triple core fusion processor devices, and fusion processors is our designator for devices that contain both Cortex-M class real-time cores and Cortex-A class application cores that can operate independent of each other. We are adding one Cortex-A32 core at up to 800 megahertz into the mix with the same configuration of real-time cores and microNPU acceleration units that you saw previously. And finally, on the higher end of the performance spectrum, we have our E7 device, which is a quad-core fusion processor with two Cortex-A32s that run up to 800 megahertz in symmetric multiprocessing configuration. This span of processing capability, combined with the other features and functionality in our device, enables our product families to cover a large range of applications and use cases based on this common architecture that I mentioned that really gives users benefit of reuse in the software investments that they make on the Alif, Ensemble, and Crescendo product families. It's very easy to migrate code up and down the performance spectrum, and the feature and functionality and processing power, as well as the power consumption properties of these devices lend themselves extremely well to essentially single chip IoT designs in many areas. I want to talk a little bit about the way that we have architected our system to achieve excellent performance on a battery. Our power management technology that we call Autonomous Intelligent Power Management, or AI-PM, is essentially a combination of very high efficient and well-designed software libraries and a very capable always-on wake-up management system that is integrated in the lowest power zone of our devices. The SoC is divided into independent power domains, and this always-on wake-up manager that is the heart of AI-PM technology controls these power domains by letting regions report into it if they are needed, and letting the wake-up manager then help control if that region needs to be power or not. This is all instantaneous, depending on use case and processing demand, and it's also completely configurable by our software. So as you can see, here's an example. This is a minimized example, so there are many more zones available in our device, but you have the wake-up manager in the same zone as our high efficiency M55 and ethos unit, as well as our modem, and then an example of the high performance zone where we have the high performance cores, other resources, memories, etc. If we look a little bit deeper into this and how it relates to the way that we have architected our environment sniffing engine, as we call the AI processing capabilities in our device, we essentially set up our high efficiency region in such a way that it can continuously sense the environment for any changes. And while it is doing that, it has access to dedicated low power sensing peripherals. So the rest of the system can be powered down while the high efficiency region listens to audio input, scans a low power parallel camera interface for changes in surrounding image, or takes sensor input from things like UARTs, SPI interfaces, I2Cs, etc. And if it detects anything that it deems to be of interest, it can then, through our AI-PM engine, wake up the high-performance real-time processing system with the faster Cortex-M55 core running up to 400 megahertz and its more powerful ethos unit to perform additional classification of that event. The high-performance system can wake up very fast. It has access to its own tightly coupled SRAM memory, so you can essentially run 2 AI models in parallel in this way. And in addition to the tightly coupled RAM that goes with both cores, both the high efficiency and the high performance core, we also have a very flexible system setup where we have access to what we classify as bulk SRAM memory that is shareable amongst all user cores in the system, and also expansion into external memory, both for NVM and for RAM. The RAM regions do have some latency penalties depending on which ones that you use, but it is entirely up to the flexible for the user to configure this in the way that best support their use case, so that they can make sure that their models have access to enough memory either on chip or by going off chip through the external memory interfaces. Here's an example use case that I want to talk about and how this can be realized with the environment sniffing engine that we have set up. This is an AI camera example with the diagram below indicating essentially a duty cycle of the system. And in a setup like this, you can have our high efficiency subsystem with the M55 and the U55 continuously sniff the environment for a trigger event. This can be either taken in via a sensor or maybe via a microphone, for instance. And you see here in the duty cycle diagram that when this sniffing occurs, the high efficiency MCU and ethos unit is leveraging the wake-up manager and themselves, of course, to perform the sniffing at some regular interval. When a trigger event is detected, the high-performance M55 And the necessary memories and other peripherals to drive that gets woken up to capture and classify an image or what the interesting event was and perform processing of that. And of course, these events can take place with a longer average time based on the specific environment that this device is deployed in. So for the demo that we intend to show you of this system in action, as I mentioned, we have partnered with ARM, and we have essentially realized this by creating a system that runs separate AI models. One of them listens for events, and if it discovers an event, it will wake up the high-performance system that will take a picture and classify that and try to see if the event was the specific event that it's looking for. You could also consider in a system like this a use case where if you get a match, if you notice that the event was something that I'm supposed to look out for, that it could then leverage our modem to call out and transmit a result. It might be the image, or it might be just a notification to the cloud via our modem. But this is not part of today's demo, as we're focusing specifically on the AI portion. And we want to show you in the demo how does a system like this perform with the Cortex-M55 core and the Ethos U55, both in terms of the speed of the inferences and the power of the inferences. What the demo will do is on the high efficiency M55 core running at 160 megahertz, we're using the DS-CNN model to do keyword spotting. And if the keyword is spotted, then that system will trigger our high-performance M55 to take a picture and classify it. The high-performance system runs a MobileNet version 2 image inferencing model that, of course, has been trained to recognize different pictures of cats. And if it finds the right cat, it will notify us that it completed its mission. We're going to run this demo now. I'm going to hand off to the ARM team. And after this is done, we're going to be comparing the performance of the M55 core, performing these tasks standalone, to if you're running this system with U55 acceleration enabled. ARM team, take it away.
So today we'll be running some machine learning workloads on the new Alif board. Here we have the CPU board, the green one, and the blue one is the base board. The CPU board has this component U1, which has two Cortex-A32s and two separate islands of the latest M class, the Cortex-M55, and both these Cortex-M55s are paired with the new Ethos U55 neural processing units. There are two main power domains on the board, the high efficiency domain and the high performance domain. The Cortex-M55 in the high performance domain is paired with a 256 MAC Ethos U55 unit, while the Cortex-M55 in the high efficiency domain is paired with a 128 MAC capable Ethos U55 unit. So we'll be using both these islands for our ML workloads, but we won't be using the Cortex-A's. On the high performance island, we'll be running a pretty hefty workload of image classification using the MobileNet V2 int8 model. This model is about 4 megabytes if you are running on M55 only, and the Vela optimized version, which uses Ethos U55, is about 3.5 megabytes. And on the high efficiency domain, we will be running the keyword spotting example, and this network is about 450 kilobytes, and the size doesn't vary that much between M55 only and the U55 optimized versions. On the baseboard, we have a few serial connections. So the yellow wires here are for our standard outputs or error streams, and this allows us to monitor all the printfs coming through. The use cases have been set up for the high efficiency M55 to trigger inferences on the high performance M55. This is facilitated by the red wire here, which is just a loopback on the GPIO lines. So the keyword spotting example is going to set one of the GPIO pins high, and the image classification example reads the other GPIO pin and decides if it should start or stop running inferences. So the whole idea is that the high performance domain is usually kept in sleep state, and it is woken up when the high efficiency domain detects something, and in our case it will be a keyword spotting network detecting a keyword, and the high performance domain then wakes up and starts running inference workloads using the MobileNet v2 model. We are also connected to a debugger via this gray ribbon cable. We are using the U-Link Pro debug probe, and we also have a scope which is connected to monitor LEDs on the board. So these two LEDs are being driven by the two islands. So the top one here is driven by the keyword spotting example, and the bottom one here is driven by the MobileNet v2 model. So this will allow us to monitor pulse widths using the scope and just verify that whatever profile we get from the software is verified using the scope as well. So we'll first run only the Cortex-M55s on both the islands. So we won't be utilizing U55 for these runs, and then we'll compare this with applications which have been built with U55 support and compare the inference numbers at the end. So we have our board connected to the ARM development studio via the Kyle U-Link Pro debug probe. And in this session, we will run the applications on M55 only. So we have several debug profiles on the left here, and we'll be using only the M55 one. So we won't be utilizing the Ethos U55 for these runs. The terminal at the top right is connected to the high performance core, and that will be running the MobileNet v2 example. And the terminal at the bottom is connected to the high efficiency core, and we'll be running the keyword spotting example on this one. So let's start the high efficiency core first. The keyword spotting example is set up to recognize the keyword yes, and it will then trigger the high performance core to wake up and start running inferences using the MobileNet v2 model. Let's go ahead and start the high performance core. It's worth noting that both the M55s have M-profile vector extensions, and we are utilizing this because we have built with CMSIS NN library support, and we have the instruction and data caches also being used by both the Cortex M55s. Okay, so now we have both the applications running. The keyword spotting example is just waiting for some audio data, and we can start injecting that. So it's starting to run inferences, and when I say yes, it goes ahead and starts triggering the MobileNet v2 inferences. So I've just paused the run for both the applications for the time being, just to look at some output. So we see that for MobileNet v2, we get an inference execution time of about 620 milliseconds. And for the keyword spotting example, we are running inferences in 113 milliseconds. And let's see what we have on our scope. Okay, so we have the yellow pulses are for the keyword spotting, and the blue ones are for MobileNet v2. So it hasn't had enough data yet. So let's just go ahead and run the applications again. And hopefully that gives our scope enough time. Okay, so we see, 116, 118, 128 milliseconds for the keyword spotting, and we see 624 milliseconds consistently for the MobileNet v2 example, and which is what we see from the software as well. And let's see what the board is doing. So yeah, we see the green LED, which is being pulsed by the keyword spotting example, being pulsed twice every second, and the orange one is being pulsed. We don't see it being pulsed because the time between inferences is quite small, but it is being pulsed by the MobileNet v2 inference runs. So we start with the same setup as before. We have the ARM Development Studio connected to the board via the Kyle-Ulink Pro Debug Probe. And in this session, we will start running applications which have been built with support for Ethos U55. So the neural network models have been optimized using Vela, and both these models will be run purely on Ethos U55 with the Cortex-M55 driving the NPU. So let's start the high efficiency core first, and that will start the keyword spotting example. And we'll do the same for the high performance core. So we should see one difference straight away, that the list of operators that we had in the previous session when we were using M55 only, in this application we just have one operation, which is the Ethos U. And same for MobileNet v2. So we have both the applications running, and we'll start injecting some audio data now. And the applications are set up in the same way, in that keyword spotting example will wake up the high performance M55 when it hears the keyword yes. Okay, so yeah, we see the keyword spotting running, and MobileNet v2 application is idle. We pause that for a second just to look at the inference time. So this is pre-processing, and the inference is 5 milliseconds for keyword spotting. So this was about 120 milliseconds when we were using M55 only. So we see a big improvement there already. And if I say yes, we see the MobileNet v2 inferences are significantly faster. So we can pause that for a second and look at the profile, and yeah, we see that we take 8 milliseconds per inference, and this was about 625 milliseconds for the M55. Let's run that. Let's see what the board is doing. So yeah, this frequency doesn't change because it's limited by the audio data injection. But yeah, on the scope, we'll be able to see that the inference execution times are indeed significantly faster. So the blue one, we see 8.2, 8.4 millisecond pulse widths, and for keyword spotting, we see 5.2, 5.4 milliseconds, which are confirmed by what we see in software as well.
All right, thank you very much, Kishit and team, for helping us out with that recording. And as you saw, we're seeing some dramatic performance improvements when we're using the U55. I'd like to summarize these results here and take a look at what that means in terms of application gains, what additional battery life, for instance, you can get out of designing with this type of AI and ML acceleration present in the system. So as you saw, even on its own, the M55 with the helium extensions is very fast at performing these tasks. The inference time on the high efficiency M55 that is doing the keyword spotting, it can do one inference every 94 milliseconds. So it's a very fast inferencing process. If you think about that in terms of how can I integrate a device like this kind of as a background piece in somebody's life where you don't realize that the job that you just asked the system to perform is being done by a machine. It's a very fast response at only 94 milliseconds. You will hardly notice that there was processing taking place there. But once we flip the U55 on, that time drops to 3 milliseconds, which is a significant improvement in that inference time. And the same with the image classification. If we run that CPU bound on our high performance M55, it takes us 624 milliseconds to perform one inference on an image. while when we turn the U55 on and run that at its full 256 max per second, that drops to 8 milliseconds. We have, and if we look at that in terms of kind of how many factors do we improve it with, for audio, that's an improvement of 28 times over the CPU bound when we have the ethos active, and the image inferencing is performed 75 times faster. You also have some power numbers here. We were measuring the power as we were executing these models in the systems, as you saw. And if we look at the average rail power draw when we have the ethos unit active, it does go up, but because the inference time drops so dramatically, overall, the amount of energy that we use per inference drops dramatically, even though we're burning more power with the ethos unit active during the time that the inference is taking place. You see that here in the table at the inference energy section. We measured that in joules, and it goes from 0.033 joules for the M55 only on audio down to 0.01. It was barely that we could record the energy per inference in that setup. And when we're doing the image classification, it drops from 0.2 to 0.003, meaning that the power per audio inference is 33 times less when we have the ethos units active, and the power per image inference is 76 times less. And that is significant because image inferencing is a pretty complex operation, especially if you have to inference on large amount of image data. So the amount of power you save here can be considerable. So we did an experiment, and we took the duty cycle that we showed on the previous slide, and we went over that, and we kind of set it up so that the sniffing interval for the background environment sniffing engine operation is set at 1 second, meaning that every second we sample the environment to see if there's an event. And then we kind of averaged out the classification events at 5-minute intervals. And then we did the math, and we added all of this together, and we tried to essentially come up with an estimation in terms of battery savings of this system. If we look at, if we were to do this type of audio inferencing to detect a keyword and then trigger image inferencing based on that keyword, how much longer could we last on a battery if we had the U55 versus if we ran this CPU bound only on the Cortex-M55. And essentially it comes out to 9 milliamp hours over a 24-hour period with ethos active if we use this duty cycle versus 247 milliamp hours if we're only running it CPU bound because of the additional time it takes to process the data. That's a 27x power saving, which essentially takes your battery life from, if we're looking at a pair of standard lithium AA batteries, around 11 days to close to 260 days of battery life. Now, granted, this is not a really real scenario. It's an idealized battery discharge cycle and things like that. And there's also a very idealized duty cycle for the application. And we're not accounting for any overhead from the rest of the system. But in terms of just showcasing the uplift that you can get from using the Cortex-M55 technology together with the Ethos U55 technology to perform AI ML workloads, you can still see from this data that the change in performance and power consumption is dramatic. And we strongly believe that this type of efficient processing is what's going to unlock the ability to truly run in-depth AI and ML use cases in these type of embedded devices. That is it for this seminar. I hope that this has created some interest with you people in the crowd that are listening to this. I'd like to thank you all for tuning in and listening to me. For more information about the demo, about Alif, about Ensemble, Crescendo, and the system that we're setting up, you can visit our website at alifsemi.com, or you can email us at contact@alifsemi.com. We'll get back to you with information. Our development kits that feature the M55 and the Ethos U55 are sampling now, and we'd love to get in touch with you. Thank you so much also to the ARM team that helped us set up and record the demo, and also for ARM for hosting the DevSummit in general. Thank you so much. Bye-bye.